Yeah, hello. Is I'm audible? Yeah. Good afternoon, everyone. I thank all the participants again to join for the lecture one. The lecture is on introduction of microgrid. Just handing over to Professor Yang Zoom. Professor, you can go ahead of sharing the screen.
Okay, thank you. Thank you, Professor Kumar. Let me share my screen. Wait a second. Entire screen. Can you see my screen now? The full screen mode?
Yes, Professor.
Okay, great. Okay, so we can start now. All right. Good afternoon, everyone. This is Yan speaking from Singapore. I'm now with Nanyang Technological University. Once again, I would like to thank Professor Siva Kumar and Professor Vindan Kumar for organizing and coordinating this GN course. As I said this morning, actually, most of the contents of this course are actually designed based on one of our undergraduate and the postgraduate course offered in NTU, Singapore. And this course is actually one of the mostly selected and popular course among our students. So I really looking forward to communicating with you on this topic. As everyone knows, smart grid is a very kind of popular area for power engineering students and researchers. So in this GN course, I will cover the following actually six topics. So I will start with a general introduction of smart grid and also energy internet. I suppose most of you are familiar with smart grid, but energy internet is actually one step further, which can coordinate multiple energy systems together. So they have different names, such as the integrated energy system, multi-energy system, so on and so forth. So for the first lecture, I will mainly introduce this smart grid and energy internet. And after that, I will also introduce the advanced metering in the smart grids because, for the smart grid, the metering communication technology is a critical component there. Then for the third and fourth part, I will introduce energy storage technologies and their applications in the smart grid because, once again, energy storage is also a critical component in our modern power systems and certainly smart grid. Then I will move to distributed generation, which is also a very important and growing component in our modern power systems. For example, our rooftop solar PV, small-scale wind turbine, so on and so forth. They are widely installed in the distribution networks. So I will also cover the distributed generation technology. And last but not least, I will introduce microgrids, which is also a very popular technical terminology as well as the industry interest nowadays, especially in Singapore, which is urban country, urban city country. We do not have high-level voltage transmission grid. Instead, most of our power grid is backboned on the 22 kilowatts distribution network. So the local industry, local power grid utility, they are more interested in the microgrid technologies. So I will introduce this microgrid in the last part. And certainly this whole course will have inputs from Professor Siva Kumar and his colleagues, including the hardware in the loop test simulation, as well as some power electronic stuff. So that is a general introduction to the whole GN course over the next few days. All right, so let's start the first lecture. Once again, briefly introduce myself. My name is Yan Xu. I'm now a professor in engineering in School of Electrical and Electronic Engineering at NTU Singapore. In the meantime, I'm also serving as a director for the Center for Power Engineering and a co-director for the joint lab between our university and the Singapore Power Group, which is a local power utility company. Okay, before I move to the lecture, please allow me to briefly introduce my university, my institute, in case many of you are not familiar with. So we do welcome students to apply for our either postgraduate program or even PhD program. All right, our university essentially originally was founded in 1955, named as Nanyang University. Okay, Nanyang means the South Pacific Sea. Okay, in Chinese. And it actually was originally a private university with the teaching language of Chinese. But after a few years later, the whole university was actually changed to an English-speaking institute. And in 1991, we become Nanyang Technological University. Although we are technological university, we actually cover all the subjects, including engineering, science, business, humanities, arts, social science, education, and even medicine. Okay, our medical school was founded back to 10 years ago. So it is actually the second medical school in Singapore. Now, I'm working in the School of Electrical and Electronic Engineering, so-called Triple E for short. This is one of the three founding schools of my university, and which is also one of the largest and highly ranked school in the world. So far we have more than 100 faculty members, more than 3,000 undergraduate students, and more than 1,000 postgraduate students. So if you look at the ranking of our university for the 4 ranking systems, we are performing very well over the last few years. And for our school, we are also performing quite satisfactory. So this is, some high-level ranking for our university and the school. So these 2 books were given to me by our founding president, Professor Chan Dao-song, because at the early this year, I was conferred the professorship endowed after his name. So he gave me 2 books introducing the history of the whole university and himself. So I'm personally very inspired by the story of the university, because as a young university, you can see with less than 40 years, it has grown very fast. And some pictures of our university, including this original main gate and this bird eye picture. This is our School of Art and Science, and this is our Student Learning Center. In our school, we have actually 6 subjects, including power engineering, microelectronics, information engineering, circuit and system, communication engineering, and control and instrumentation. So you can see that we cover all the areas in electrical and electronic engineering. For myself, I belong to power engineering. And in this subject, we have a center, so-called Center for Power Engineering. Now we have 11 faculty members at the rank of assistant, associate, and full professors. We have 6 IEEE fellows and 1 foreign fellow of Royal Engineering of UK. So we work in power systems, power electronics, electric motors, and drives. We have a number of advanced research labs, including the joint lab between our university and the Singapore Power Group, Rolls-Royce NTU Corporate Lab, Clean Energy Research Lab, Water and Energy Lab, IoT Lab, so on and so forth. We have, in terms of the research students and research staff, we have over 100 people. And our annual research funding is around 5 million Singapore dollars from government agencies and the industry per year. And we have been, actively working on high-level research works. Every year, we probably will publish around 80 top-tier papers in journals and conferences, and we also licensed our IP to the local industry for practical deployment. And also we have patents, we have many research outputs every year. So that is an overall picture of my university and my school as well as my center. Okay, after that, let's continue with the lecture today. So here is outline. I will start with a brief introduction of the power systems history, giving you a general sense that how power grid is evolving. And after that, we will introduce the concept of the smart grid, including its major features in power generation side, power demand side, as well as the metering side. Third part, I will talk about power system security because at no time the security of the power system should not be can be compromised. When we incorporate more and more renewables, when we have more electrical vehicles, when we have more flexible loads, we should always maintain the security of the power grid at a high level. That's why I have to put the power system security here in the first lecture. And last but not least, I will introduce the new concept, relatively new, energy internet. This is actually the next step of the smart grid, which is beyond electric networks, because it will also incorporate other energy networks, such as gas networks or even transportation networks, because we have more and more electric vehicles on the road. Right? So this is a general outline of the lecture today. We have 1.5 hours, so probably we will stop around 40 minutes and give you 5 to 10 minutes break. All right, so the whole lecture will be divided into 2 sessions. Okay, so to start with, let's have a very quick look at the first power system in the human's history. That was almost back to 400. How many years? 142 years ago. All right. So the first power system was actually built in United States, New York City, which has a DC generator supplying 85 customers. Most of them are actually electric light through a kind of electrical cable over an electrical pole made of wood. Okay, so this is the first power system in the human's history. So very clearly, you can see that the generator is actually a DC, okay, so-called standing for direct current. Now, after that, the power system has significantly evolved and changed. One of the most important change is to switch from the DC system to the AC system. Okay, AC here stands for alternating current. So there was actually a very famous story behind for this switching. So everybody, I suppose you know the Thomas Edison and his employee Tesla, right? The very famous electric vehicle brand Tesla was actually named after this genius engineer. Okay, so at that time, the power grid is dominated by DC, okay, because at the very beginning, the generators are DC. Then the question is, when we want to transmit large scale power over long distance, right, we have to increase the voltage, right? Because if the voltage is too low for longer power transmission, it will have much big power loss. Okay, so in order to reduce the power loss and increase the power transmission capacity, we have to increase the voltage. Now, question is, how can we increase the high voltage? Now, somebody may say that, okay, we can use a generator that can directly produce high voltage current. Yes, this is true. However, for the DC generator, it's not easy to do that because for the DC generator, there will be a kind of brush. So it's not easy to increase the DC generator's voltage to a very high level. Now, what else can we have? So we can have actually a transformer. Okay, I suppose everybody knows transformer, although this term has different meanings, right? For the computer science, transformer means a machine learning model, right? For Hollywood movie fans, transformer is a movie. But for power engineering, transformer is to, step up or step down the voltage, okay, from the primary winding to the secondary winding. Okay, I suppose everybody knows the working principle behind it. Now, with transformer, we can increase the voltage freely, and we can increase the voltage from low level to a very high level, depending on the numbers of the windings at both sides. But the question is, transformer works on the alternating current based on the electromagnetical principles, right? So for the DC system, transformer cannot work. Now, next question is, in order to use transformer to increase the high voltage, we have to have a AC system. And at that time, Tesla has invented the AC induction motor, which can produce AC system and then AC electricity, and then connected with transformer, we are able to increase the voltage to a very high level. And with that, we are able to transmit the power, the electricity, from remote place over a long distance. So that is, motivation and history behind the AC power system. But clearly, Edison is a boss of the company, so he certainly does not like the AC system to overtake. So there actually was a kind of battle or even so-called war behind the two famous guys. So actually, there was a Hollywood movie telling about this story, so-called the Current War. If everybody is interested, you can search online. You probably can see how Thomas Edison and Nikola Tesla were fighting against each other on this electricity. So that is some, interesting story behind the DC system and AC system. And after that, after the system power grid becomes dominated by AC, there are many other new developments, especially for the voltage, transmission voltage. So the voltage was continuously growing. Nowadays, we can achieve 1,000 kilowatts for AC. And we can even achieve plus minus 800 kilowatt DC, okay, for very long distance power transmission and with low power loss. Now, I suppose some student may ask, okay, sir, you just mentioned the power grid was dominated by AC, but why we still have high voltage DC? Okay, now answer is, compared with AC system, right? AC system, we need to have a three phases, okay? Because the generator, when it produces AC current, there will be three phases. But you can imagine that for the transmission grid, every time we have to build three transmission lines. Well, for the DC, actually, we only need a single phase. Okay, we only need a single phase. So compared with the kind of construction or investment cost, when the power transmission distance is beyond a certain limit, if I remember correctly, probably 400 kilometers. Behind 400 kilometers, DC system is cheaper than AC. So that's why high voltage DC system are still being used nowadays, especially for extra long distance power transmission. Okay, so that is the difference between HVAC and HVDC. And later on, people want to connect the regional power grid to be a, entire or interconnected giant big power grid so that the whole reliability and the economy can be improved. So nowadays, power grids at the national level, they are mostly connected together to be a giant power grid. And besides, traditionally, the power industry was regulated, kind of monopoly industry. However, in order to encourage competition and increase the market efficiency, the electricity market concept was introduced since 1990s. Okay, so nowadays, in many countries in the world, the power electricity market are there, including Singapore. Okay, Singapore, we have a wholesale electricity market. But no matter how the power grid was changed and evolved, generally speaking, the whole grid can be divided into three segments, which are generation, okay, transmission, and distribution. Okay, so the electricity is generated by the power plants. Okay, after that, the electricity will be stepped up to a high voltage with the transformer, and then transmitted over a long distance high voltage power lines. And near the load, the voltage will be stepped down to a low voltage level and then supplied to our customers. Then the customers can be generally classified into industry customers, consumer customers, and the residential customers. And of course, the load pattern and load characteristics of the three types of the customers are totally different. That's why in the smart grid area, we have to analyze the characteristics of the customers so that they can also participate in the power grid operation and control. So that is one of the very important concept or motivation for the smart grid. Okay, after reviewing the history of the power system, let's take a look at the smart grid. I suppose everybody has noted that I have put a quotation mark for the smart grid because for me, I think smart grid is more like a concept instead of a concrete physical system. But certainly, smart grid has to be a power grid. But the question is, how can we define the grid to be smart or not smart? That's why sometimes I prefer to put a quotation there in order to denote this is kind of a concept instead of a very concrete thing in reality. Now, where is the concept of the smart grid coming from? Actually, if you look at the history, this concept was widely known worldwide since 2009. And actually, this concept was initially proposed or promoted by the US President Barack Obama. I'm not sure how many of you know him. He was actually the former president before the first tenure of Donald Trump, if everybody knows it. So since his first tenure, 2009, when he just started his position, he wants to, put some economic incentives to the U.S. economy. Now, one of the very quick and effective measure is to do the infrastructure investment. Right? We can upgrade our power grid. We can upgrade our transportation road. We can upgrade our, let's say, airport, so on and so forth. So when we invest in this critical infrastructure, we can, incentivize our economy. So that is a general rule in the economy area. So since his first tenure, he actually announced a 3.4 billion US dollar investment to the power grid. Then at that time, he called it smart energy grid. So to me, I think that is the first time when the concept smart grid was made worldwide known. Okay, because his impact, because this very big investment. Now, very, very quickly, everybody, especially in the power engineering sector, start to know this concept, smart grid. And for myself, in 2009, I just started my PhD program. Then I clearly remember that once a day when I was sitting in the lab, when I reading the literature, somehow a kind of new concept, I remember it was a news or article pop up, then saying that, okay, USA is now developing smart grid technology. So this is the first time I saw this concept. But at that time, I did not care much because at that time, many, many things are called smart. If you remember, if you are at the same age with me, at that time, we have the so-called iPhone 3 at that time, which is called a smartphone. And later on, we have a smart TV. We have like everything is called smart. So to me, I was not surprised to see smart grid because everybody want to call the thing smart. But then the question is, how can we define the grid is smart or not? Just like how can we define a phone is smart? Now, at that time, I remember the criteria for smartphone is that first of all, you need to have a touch screen, right? You need to have a camera. You need to have a lot of advanced app, so you can do a lot of new functions. So to me, I think, okay, in order for a power grid to be called smart, they must have more functions, right? They must have more functions. So at that time, I and my supervisor, we start to read a lot of technical reports. I remember one report was published by USA, EPRI, and Electric Power Research Institute. And in that report, they have defined some criteria, or so-called new functions of the power grid. Okay, then after you can see 7 years later, the same president Obama, when he was stepping down, he announced another investment for the power grid, another 3.5 billion. Okay, so you can see that he's really a big fan for the smart grid. And I think owing to his effort, owing to his kind of investment, the whole power industry worldwide have like um, received much more attentions from the government, from the industry, from the agencies, or even from the researchers. Okay, so I think that is a general story behind the smart grid. Now, I wonder, I suppose many of you are curious, why do we need to develop smart grids? As I just said, one of the motivation is to do the investment and inventivize the economy, right? But is there any technical motivations? Actually, yes, certainly there is technical motivations. So I think the first and most important motivation come from the environmental pressure, right? Everybody now knows we are experiencing global warming, right? We have a kind of temperature increase. We have carbon emission. So much carbon emission make the global temperature increasingly grow, right? Then we have like a traditional fossil energy crisis. We are kind of exhausting the uh, energy resources, the oil, right, the coals, so on and so forth. So we have to find a way to address this environmental pressure. We have to find some new energy, alternative energy. Okay, so that is one of the motivation. Another motivation is for the many developed countries, especially for the USA. You can see that the first power grid started back to 140 years ago. So you can imagine that how old the power facilities are in these developed countries. So another important motivation is to modernize the power grid, to replace these old electric facilities. And in doing this, they can also create new jobs, right? They can also promote the economy, right? So this is the second motivation. And third motivation is to reinforce the network, because originally sometimes our power grid are not strong enough, okay, especially in developing countries. Okay, sometimes we may experience outage from time to time. That is because our network is not strong enough, not resilient enough. So we have to invest in the network to reinforce itself, to make it stronger, right? So in many countries, they have invested in a high voltage transmission uh, grid, and also they have reinforced their distribution system. So the network reinforcement is the third motivation. And some other motivations come from the load side. Right nowadays, we have many new types of the load, such as electric vehicles. Right, originally, vehicles is just a transportation tool. Right, it has nothing to do with our power grid. But now the vehicles have to charge its battery from the grid, so it becomes an electric load. Okay, and our power grid was not designed for such a kind of charging loads before. Now, if the electric vehicle load, the number of the electric vehicles continuous grow, whether our power grid is able to host them, this will be a big challenge. Okay, and besides, some of our customers, they are flexible. Okay, their load can be controlled. Their load can have certain flexibility, right? So our power grid also want to welcome such flexible load to support the grid operation and control. Okay, and certainly there are many other motivations, but I think these four motivations are most important. Okay, coming from the environment, coming from the power grid, coming from the load. Okay, now after saying so much, I suppose everybody will be very curious. What does a smart grid look like? Okay, As I said, smart grid to myself, I think it's more than a concept, not a concrete kind of physical system. We cannot say, okay, this grid is smart, that grid is not a smart grid, not that way. We can only say that, okay, this power grid has smart grid functions or have smart grid features. That is my personal opinion, okay? But certainly it's open for discussion. So here I just list a high-level illustration of the smart grid concept. Okay, so if you look into this diagram, look into this graph, you can clearly observe that, okay, we have generators, traditional generators, thermal power plant, hydropower plant, they are all traditional. We have transmission network, transmission towers, distribution grid, transformers, then the load, all right? So certainly everything remains a power grid. But what are new things? Okay, clearly you can see that we have now renewable energy resources. For example, wind power and solar power. So at the generation side, we will have more clean energy, renewable based energy. That is the first difference between a smart grid and a traditional power grid. And out of that, what can you observe? You may note that, okay, we have energy storage, right? We have like a demand response. We have electric vehicles. These resources are installed at the demand side. Okay, so traditionally we have to keep our customers' lights on, right? But nowadays, the demand, they have certain flexibility. They can respond to the power grid. The electrical vehicles, they can charge the power at different times. And they may even install the energy storage system to charge and discharge when there is a need to do so. So at the demand side, we also see a lot of new things. All right. And on top of it, what's that? You may note that, okay, here we have a so-called PMU, a kind of very advanced metering technology, which can measure the synchronized and real-time data of the system. This PMU is a short of phasor measurement unit, which can measure the phasor data of the grid. And you can see they are synchronized by the GPS satellite so that they can provide you the time synchronized data of the grid. In the past, this is impossible because we only have SCADA system, which can only measure non-synchronized and low sampling data, right? And what else? Okay, last but not least, you may note here smart meter. Okay, smart meter is installed in our household level. Okay, so in the past, in the residence, we only have a kind of mechanical meter, right, which can only tell you how much energy you have consumed. And based on that, you pay the electricity bills to the company, your utility company. But now smart meters can measure the power consumption profile of the customer. So they will give you more information. And with this smart metering data, we can do more functions. That is another very big difference. Okay, so based on this picture, let's just take some realistic figures. In terms of the renewable energy, you can see that how rapidly the renewable energy capacity is growing. Okay, not to mention the traditional hydropower. We just look at the solar and wind power. You can see how fast the solar and the wind are being installed in our power grid. Okay, this data come from the World Economic Forum. And then how about the electric vehicles? You can see that a dramatic increase over the years, right? We have battery electric vehicles, hybrid electric vehicles, right? You can see their market share nowadays, especially in many countries, USA, North Europe, right? Even in China, Australia, a lot of electric vehicles. Okay, in our university, we are actually collaborating with BMW to develop electric vehicle technology. Okay, and smart meters. Okay, smart meters, you can see that compared with the traditional mechanical meters, smart meters is more digitalized. Now, in different countries, areas, you can see how fast smart meters are installed, right? Especially in the new development, I mean, uh, residential developments, most of them are actually installed with the smart meters. Okay, so if we want to make a summary of the smart grid, okay, just now we have shown a big picture, right? But what are the summary for the smart grid? Or in other words, what are the key features, technical features of the smart grid? So if I could summarize, I will start with the generation side. At the generation side, we have a high-level integration of the renewable energy resources, particularly wind and solar power. That is the first feature. A second feature, we have more participation from the demand side resources, such as the flexible load that support demand response, okay, electric vehicles, smart appliances, and even energy storage, the batteries, they are all installed at the demand side and they can participate in the power system operation. So I think that is the second difference. The third difference, just mentioned, we have new meters and communication technologies. So the third feature of the smart grid is the widespread deployment of the advanced ICT, information and communication technologies, including but not limited to smart meters, phase measurement units, advanced metering infrastructure. Okay, so with all of these three features, we can call a power grid to be smart. That is my personal summary. But if you look at other technical reports and the papers, more or less, they have these three major features or functions. Now, clearly, smart grid can bring a lot of benefits to us. Okay, at the generation side, with more and more renewable energy resources, we can reduce the carbon emission. Right, they are environmentally friendly. All right, and at the demand side, if we have more controllable resources, they can help the power grid. They can support the power grid's operation and control. For example, if there is excessive wind and solar power generation, we can use this renewable power output by charging our vehicles, right? Or if there is less power generation or power deficit, we can stop charging of our vehicles. So you can see that this demand side resource, they can play a role in power grid. And in terms of the ICT technology, certainly they can provide more data and more information about the power system and about the customers. And with all of this data, we can extract the useful knowledge, information, and then we can design different tariff schemes. We can also support the condition monitoring of the grid. We can also increase the situational awareness of the system security, so on and so forth. So clearly, the smart grid will bring many benefits in the three perspectives. Okay, so here I want to just list some useful websites. Some of them actually come from Singapore because, as I said, this lecture slides was designed based on one of our coursework here. So you can see we have a Singapore Energy Market, Singapore Power Group. They actually published a lot of useful data. And in terms of Australia, there is Energy Market Operator, AEMO. They also publish the electricity load data, market data, so on and so forth. In USA, Department of Energy and Electric Power Research Institute, EPRI publish a lot of technical reports. Okay, you can definitely download many useful reports there. European, there is a European Energy Consortium. Okay, and we also have a international institution for electrical and electronic engineering, IEEE. Now in IEEE, we have a Power and Energy Society, PES. Every year, PES hold many conferences. There are also numerous digital resources that researchers, engineers, students can benefit from. Okay, but certainly, if you are doing power electronics, there are IEEE Power Electronics Society, Industry Electronics Society, so many societies that are related to power and energy. And at NTU, we also have Energy Research Institute, ARIAN. So in ARIAN, we have a lot of flagship research projects. Later, I will introduce some of them. We also published many useful reports. And also in Singapore, we have this consortium, Bridging Smart Grids and Power Electronics. We call it SPECS. Okay, SPECS is a kind of industry-led consortium with collaboration of university and the research institute working on this topic. Last but not least, I have my own research group website. I usually publish our research papers and my presentation slides there. So if everybody are interested, you can go to this website. You can find many useful information there. Okay. Okay, and here are two very good report published by my university. One is about the smart grid, so-called Grid 2.0. Another one is related to power electronics. Okay, advanced power electronics enabler for energy transition and efficiency. So in these two reports, we have actually introduced a lot of basic concepts and state-of-the-art technology, as well as demonstration projects in smart grids and power electronics. So everybody, you can go to this website to download these two reports. These two reports are more for kind of fundamental concepts. They are not kind of technical papers. So I suppose everybody can quickly understand these two reports. Okay, so now we just have 40, we just finish the first two sections, and it's exactly 4:40. So I will propose maybe 5 or 10 minutes break before we go to the next session. Is that okay, Professor Kumar?
Yeah, yeah, fine, fine, fine.
Okay, 5 or 10 minutes, do you think?
Yeah, fine, fine. 5 minutes is fine.
Okay,
It's
so
up to
5
you.
minutes. Let's go back. Let's come back at 4:45. Okay, 4:45. Thank you.
Hello.
Yes.
Hello.
Hello. No sound.
No, no, it will be start at 2:15.
Okay, okay. Thank you, thank you.
Okay, let's go back and continue with the third session of this lecture. So I will talk about power system security. As I briefly mentioned at the very beginning, right, the top priority of a power grid is to keep the lights on, right? So we have to maintain a high level security of the system. Or in other words, when we develop smart grid technologies, when we deploy more renewable energy resources, we should not compromise the security of the grid. Okay, so that is why we have to introduce the power system security. However, I wish to let you know that during the operation of the grid, security certainly is our top priority. However, we also have other objectives. Right? For example, as I said, we want to have more renewable energy resources. We want to utilize more wind and solar power to achieve a low carbon power grid. And in the meantime, we want to have an economic objective when we operate, dispatch, and plan the grid. In other words, we want to minimize our operation cost. We want to minimize our investment cost. But unfortunately, these three objectives, they are actually conflicting with each other. Why? For example, if we want to maintain a very high level security, certainly we can invest more on our power grid infrastructure, right? We can add more lines, we can have more power generators, okay? But certainly it will sacrifice economy, okay? When we want to have more renewable energy resources, we have to place more power reserves because wind and solar power, they are intermittent and they are random. Their power output is controlled by the weather, the solar irradiance, and wind speed. So their power output is always fluctuating. And in order to cope with this, we may have more power reserves from the traditional generators, or we have to install energy storage system. But all of this will come at a cost. So in order to utilize more renewables, we also need to sacrifice economy. And besides the renewable energy resources, they may have impact. They may have some impact on the system security because the power output is always fluctuating, not stable, right? So you can see these three objectives are conflicting with each other. And this is sometimes called conflicting triangle for power grid. Now, our objective is to make a balance between the three. Okay, we want to achieve an optimal balance, which has a high level of security, a high level of low carbon, okay, and also a reasonable economy objective. So that is the purpose of our power grid operator and planner. Now, so today I just focus on the security and give you a sense how the security is defined and why security is impacted by the renewable energy resources. So this is a general, once again, this is a general architecture of the power grid. We have generators, right? Be in traditional power plants and the renewables, wind and solar. Then we have transformer, transmission tower, line, cables. Then we have a step-down transformer and connected to the load. Okay, so everything is connected with each other. However, unfortunately, in reality, all the equipment, all the infrastructures are exposed to the possibility of contingencies of faults or disturbances. For example, there might be a short circuit happened in the power transmission line, right? Caused by let's say a rainstorming, or even caused by a tree, okay, a tree branch touching the transmission line. It can cause a short circuit. And it may also caused by malfunction of the operator. Okay, accidentally I wrongly press a button, that may also cause a disturbance. Okay, and also there are many other disturbances happened from time to time. So the power grid should be able to maintain a secure electricity generation, transmission, distribution, and consumption process, even with these disturbances. Okay, even with these disturbances. However, it's always easier to say than doing, right? If you look at the history, okay, since 2000, the new century, you can see around the whole world, almost every 2 to 3 years, there was a major nationwide blackout happened, covering all the countries, developed countries and developing countries. Now, one of the most famous one is back to 2003 in North America. You can see this is the satellite map. Before the blackout, you can see the lights are quite shining. Right? After the blackout, you can see most of the areas become dark. And this is one of the most serious blackout in the history, which affect 15 million people. Then after that, you can see 2006, Western Europe also experienced a big blackout affecting 10 million people, followed by Brazil, okay, and even India, 2012. I'm not sure if you have experienced that. Then after that, Hurricane, okay, South Australia, and very importantly, this Hurricane blackout was considered, caused by cyber attack. Okay, it was considered by cyber attack, and the South Australia blackout was triggered by wind power, large-scale wind farm loss after a kind of very heavy rainstorm. Okay, and even in Singapore, okay, 2018, we also experienced one of the most serious blackout in our country. And I personally experienced that during 1 a.m., midnight. Actually, I personally didn't experience, but after the next day, my student, my postdoc fellow, they came to my office. They said, "Oh, sir, yesterday evening during a.m. or 2 a.m., there was suddenly no power, no electricity." Okay, I said, "Oh, I don't know because I was already in sleep." Then they just tell this to let me know that they are so hardworking because they are still working in the computer until 1 a.m. So that one was the most serious blackout in Singapore. Although Singapore, the power grid reliability is almost the top in the world. Later, I will show these numbers. And then you can see New York, okay, UK, all blackouts. South America, okay, it's also considered by cyber and physical attack. And 2021, Texas, USA, very big blackout was caused by extreme weather. And certainly there will be many more blackouts happening, okay, in the near future, almost every 2 to 3 years. So in other words, we cannot prevent the blackout to happen, but we can prevent the impact of the blackout. We can try to minimize the impact of the blackout. Okay, so how can we do that? So first of all, we need to understand the definition of the security. So roughly speaking, the security of the power system is the ability of the system to withstand disturbances without interrupting customer services. Right? So in other words, the security means the ability of the grid to keep the lights on. But how can we do that? How can we improve that? Now, there are numerous criterias, metrics, and certainly there are different technologies from the control, from the planning, from the operation to increase the reliability. But before that, let's just take a look at several widely used index to quantify the security. Okay. Well, in security, sometimes we use the reliability metrics to denote how secure the power grid is. The two most widely used metrics are SIDI and SIFI. Okay, SIDI stands for System Average Interruption Duration Index. Okay, that measures how long is the outage for a power grid over a certain period, let's say every year. Okay, another index is called SIFI, which stands for System Average Interruption Frequency Index, which measures how many times a system will have a blackout. Now, if you look at Singapore's reliability index, okay, in terms of SIDI, in the past few years, for example, here, 18 to 19, only 0.8. In other words, in the whole year, we only experience less than 1 minute blackout. Okay, less than 1 minute blackout on average. Now, 20 and 20, 19 and 20, it reduced to 0.59 because the blackout happened in this year. Okay, the blackout I just mentioned happened this year. And in 20 and 21, it continued to decrease to 0.15 minutes. Okay, so that means it's just several seconds blackout for a year. Now, in terms of the frequency, okay, the times in 20 and 21, 0.0073. Okay, almost nobody experienced a blackout on average. So that is kind of some index, a performance index for Singapore's power grid reliability. However, you can see that the 2018 blackout still has a very, very big impact. It lasted for 38 minutes, affected 19 areas with totally more than 146,000 customers. So it's almost the most serious blackout in Singapore's history. Now, I was interviewed by our local journalist, Straits Times, to talk about this blackout. So to me, I think the whole blackout was just restored after 38 minutes. To me, I think this is very fast. All right, this is very fast. Now, in order to further maintain the reliability of our grid, so the Singapore Power Group and the local government agency, they want to do more research. Okay, why we are studying smart grid? Because as a student, as an engineer, as a researcher, we want to contribute to our power grid, maintain its reliability, improve its reliability. So back to 3 years, actually 4 years. 4 years, our local utility company, they have invested 30 million Singapore dollars to our university, and we have funded such a joint lab, okay, joint laboratory with the company to work on the power grid, power equipment reliability. Okay, so this is a joint lab in our university, and I am actually one of the co-director of the whole lab. So in this lab, we are particularly looking at the power equipment reliability, including the asset health modeling and planning, component degradation studies, failure mode analysis, as well as condition monitoring. Okay. The whole purpose is to improve the reliability of the equipment so that the reliability of the grid can be maintained. Okay, so that is just to give you some sense of how much effort, Singapore is putting to maintain the power grid reliability. Now back to the concept. Well, security generally means the ability of the grid to keep lights on, but technically there are certainly many, many criteria, right? So generally speaking, the security can be divided into two big categories, being static security and dynamic security. Now, static security only measures the bus voltage magnitude and the line flow. Okay, it has, once there is like a bus over voltage, under voltage, or branch overflow, it's considered to be static insecure. And another more complex criteria is dynamic security. It measures the dynamic behavior of the system. And sometimes this dynamic security is also called stability. Okay, if you are a researcher, if you are a PhD student, I suppose you are familiar with this concept. And looking into the stability, there are more categories focusing on rotor angle of the generators, frequency of the system, voltage of the buses, right? And under each of them, there are more subcategories. So if you are a postgraduate student, PhD student, and stability can be a very, very good and deep research topic. Okay, so now next I'd like to mention how the renewable energy resources will impact the power system stability. I think intuitively speaking, everybody can understand, okay, wind and solar power, they are fluctuating, right? They always produce intermittent and random power output. And this certainly will affect our power grid. Now, here is an illustration. This is the wind speed. You can see that over a very short time period, you can see how fluctuating the wind speed is. And correspondingly, the wind power output is also highly stochastic. And looking at this solar power output, right? During the evening time, there is no power. And when the sun rises, you can see the power output of the panels will increase. However, suddenly if there is a cloud coverage, immediately the solar irradiance will drop and the power output will drop correspondingly. Now, you can see that the total speed of the power reduction could be very high, almost 15% every minute. In other words, in just 1 minute, 15% of the solar power can be lost after a cloud movement. Now you can imagine how much this wind and solar power will change our power grid, right? So that is on the static characteristic, only on the power generation perspective. Then the renewable energy resources will also significantly challenge the dynamic characteristics of the grid because this wind and solar power, they are interfaced through the power converters. Okay, the power converters works on the principle of very high frequency switching of the IGBT materials. They are unlike the traditional synchronous generators. So if they are interfaced through the power converter with the grid, this power converter will change the dynamic behavior of the grid. Okay, so that's why later on, Professor Kumar and his team will also teach you some power electronics stuff, including the simulation, modeling, and analysis. Okay. Now, while smart grid are good, for the first place, they will also introduce some challenges on the other hand. Okay. Now, first of all, the renewable energy resources, they are environmentally friendly, which are good, but in the meantime, they are highly uncertain and difficult to predict. So they will introduce considerable operational uncertainties to the grid. This is one of the challenges. And besides, they are connected through power converters, which will also deteriorate the system's dynamic performance. Okay, for the second disadvantage. And besides, when we have more distributed generation on the rooftop solar PV, so on and so forth, they will also affect the distribution network. And last but not least, the smart meters certainly can help us to collect more data, but in the meantime, they may also introduce cyber attack risk, right? If there is a hacker, he is able to inject the false data or attack to the smart meter. They may also affect the customers, right? Besides, the data of the smart meters probably can be stolen, and this will cause privacy concerns. Okay, so here I just listed some downsides of the smart grid. And I want to just let you know, okay, when we have a good technology, it will have, a good side and also the dark side. That's why everybody will have to be careful about this. And that's why as a student, researcher, and a professor, we have to maximize the upside of a technology and minimize the downside of the technology. Okay, so that is my personal perspective. Okay, then last section, energy internet. As I just mentioned earlier, energy internet is, the next step of the smart grid. Then, once again, you may wonder how this concept was proposed and who proposed it. Okay, now this time, the energy internet was proposed also by a famous guy, but not the U.S. president. Instead, this guy is a Nobel laureate awardee in economy. Okay, Nobel Economy Laureate awardee. So-called, his name is Jeremy Rifkin. Okay, he has published a book called Industry Revolution. Actually, the so-called third industry revolution. Okay, third industry revolution. And in this book, he envisioned that in the future, uh, people can produce their own green energy in their homes, offices, and factories, and they are able to share the energy with each other, just like internet. So he called this new paradigm as the energy internet. Okay, energy internet. Now, under this new concept, many people, researchers, and industries, they have proposed different conceptual design of the energy internet. Now, here today, I just want to show a very general and mostly popular, acceptable version of energy internet. Now, I give you maybe 10 seconds to look into this picture, and you probably can find some differences and similarities of this one and the energy internet. All right, I give you 10 seconds. Now, I suppose, first of all, you may note that, oh, okay, there is still central power plant, there is power system network, there is transmission line, distribution line, solar PV, wind. Okay, so in the middle, this is a power grid. Okay, it's a kind of smart grid version type of power grid. And on the left, you can see, okay, there is electric vehicles and the EV charging infrastructure, then transportation network. Okay, so the electric vehicles and transportation networks, they are actually interfacing with the power grid through the charging infrastructure. Right, this is on the left. On the right hand side, what are they? They are power to gas, they are gas network, they are gas storage, they are kind of a gas pump, they are CCHP, standing for combined cooling heating power plants, which can simultaneously generate electricity and heat. Okay, so you can see that, okay, this gas network is interfacing with the grid through CCHP plant and also through power to gas facilities. So you can see that in this version, we have a very big energy system, including power grid, transportation grid, and the gas grid. Now, this combined and integrated big energy system can be considered as energy internet because they are interfaced together. Okay, people are generating and consuming this electricity, the gas, and on the road, right? So we may consider the three individual systems together as a whole for their analysis and for their operation control. And the final objective is to improve the overall energy efficiency. So that is why energy internet is proposed. But certainly for this very big system, we need to have more advanced monitoring, communicating, control technology such as cloud computing, internet communication, big data analytics, um, artificial intelligence, right? Everybody can put latest technology there. So if you look at the evolution path of the energy system, the conventional power grid started from 1882. Okay, it is just have traditional fossil fuel generators. And after that, 2009, smart grid, we have more renewable energy resources. Then in 2015, energy internet, we have even more energy carriers, including the transportation grids, gas networks. Okay, so this is the general evolution path of our power and energy system. Now here, this is a table that compares the smart grid and energy internet. You can see they are very different, although they have similarities. In terms of the renewable penetration, The smart grid remains dominated by fossil fuels, traditional power plants, but the renewable energy is growing. However, for energy internet, the renewable energy may be dominated, and the fossil fuel maybe only share a small portion. And in terms of the energy generation, right, smart grid still rely on the big power plant, centralized power plant, but it will have more distributed generation resources. However, energy internet will be different. It will have more and more renewable distributed energy resources installed at the load site, rooftop solar PV, right, microgrid, and small wind turbine, so on and so forth. And the physical system, smart grid only contains power grid, but energy internet has other energy systems. And in terms of ICT networks, smart grid is using a closed industrial network, but the energy internet may be more open. It can have internet as a communication technology. Just now, I see some students ask a question: is the energy internet prone to cyber attack? My answer is yes, because we will use more and more different communication technologies. For example, internet. And certainly for internet, it is less secure than the closed industry network. That's why cybersecurity is becoming a very, very important topic in industry academia nowadays. That is because people want to use this internet with our electricity network. A smart grid only carry electricity for sure, but energy internet will also carry chemical energy, thermal energy as well. Okay, then lastly, for the system control and operation, smart grid relies on the traditional hierarchical control of the grid. And it has a local coordination, but it's not much. But for energy internet, we can apply all the advanced technology, big data, artificial intelligence, wide area control, so on and so forth. So that is the comparison, difference between the two. Now, actually, after the energy internet was proposed, there are already a lot of demonstration or research projects or industry projects around the world. Now you can see USA, they focus on the hardware design. There is a project called Freedom, which is developing the so-called energy router. It's a kind of a advanced power converter that can interface immediately AC and DC source and do the conversion. While in Germany, there is a project called E-Energy. It focuses more on the transaction and the trading of the energy. And Australia, you can see there is a power gas network coordination. Okay, it focuses on the merging or coordination of power network and gas network. And in China, there are many other. China focuses more on the energy system connection. Okay, energy system connection. And this is a kind of illustration of China's global energy interconnection. Okay, last month I was in a conference in Singapore, and I see a presentation from this institute. They are introducing their ambitious plan to connect the power grid all over the world through high voltage DC and high voltage AC technology. Okay, and Australia, as I said, they are interfacing a power network and a gas network. So for me, I was involved in this project when I was doing my PhD and postdoc in Australia. So at that time, we are analyzing both gas network and the electricity network, and we want to make the optimal investment for the gas storage and the CCHP plant planning. Okay, and in Singapore, Singapore focuses more on the distributed energy resources because we are not a big country. We are just a city scale country. So we focus more on rooftop solar PV, energy storage system, and electric vehicles. Okay, electric vehicles. And here at my university, NTU, we are leading a research and development and demonstration project called READS, standing for Renewable Energy Integration Demonstrator Singapore. Okay, so this is a research and development platform for different distributed energy resources technology. Here are some pictures. You can see this is the project is on this island. Okay, you can see some pictures. Now this is a map of Singapore. Okay, this is our university here. This is the land where we are doing this demonstration project. We have many industry collaborators from all over the world. And for this project, you can see we are designing, we are constructing a hybrid microgrid with different renewables, energy storage systems, fuel cells, and diesel generators. Okay. And we have many companies collaborating with us who are investing in solar panels, wind turbines, energy storage, different technologies, batteries, supercapacitors, flywheel, and the fuel cell, hydrogen electrolyzer. Okay, and the DER, we are collaborating with Rolls-Royce for the diesel generator set. And we are doing system controller, energy management system, and we're also doing electrical vehicles, all right, multi microgrid interconnection, and we're also looking at the techno, enviro, and the social impact study. So this is a very big project. You can go to this website to learn more information about it. More pictures, okay, solar panels, wind turbine, and diesel tank, okay. Switch gear, medium voltage, low voltage, all right, panels, solar panels, and we have this hydrogen electrolyzer, and we have different batteries in LFP, lithium LFP, lithium NMC, and we also have lead acid batteries installed in the system. Okay, you can see here. Electric vehicles, we have a fuel cell electric vehicles, which is supplied by this hydrogen electrolyzer. Okay, then we have the generator set as the main power source. Okay, solar panels of different technologies. Yeah, that is something about a project happening in Singapore and in my university. Then I will also provide some website for you guys, the students to learn. For your homework readings, I suppose everybody nowadays are familiar with net zero or carbon neutrality, right? Energy transition, new power systems, so on and so forth. Different countries, they may have different names, but essentially they are all related to smart grid and energy internet. So I leave you guys to read this website for your homework. Okay, I think that is the end of my slides. We still have several minutes. I would like to answer some questions from the students. Okay, so let me see the questions. Can you share the Google? Oh, okay, that is other thing. Is energy internet market? Oh, okay, this one I have just answered, right? Certainly yes, because when we have more communication technology, certainly the risk will grow. But in the meantime, we have more advanced, we have more defense, we have more detection, cyber attack detection and defense technology. So we can protect our system better. Okay, I will share these slides with Professor Kumar, so you can directly refer to the slides deck, okay, instead of just typing this website here. Later on, we'll send these slides to our course coordinator, Professor Kumar.
Yeah.
Okay, so any more questions from the...
Professor, I have one question.
Yes, please.
Is the standards which you have mentioned, SAIDI and SAIFI, are the standards which they can measure the reliability of the power grid?
Yeah, you mean the standard?
Yeah.
Okay, standard. Which standard are you talking about?
SAIDI, you have mentioned in the SAIDI.
Oh yeah, SAIFI. Here, yes.
These are the, all over the world, globally, it is followed to check the reliability.
Yes. If you look at the SAIFI here, there is actually a report published by DNVGL. Singapore's electricity grid is actually the top among the major cities in terms of the SAIFI. Yeah, so this is, a standard. It's a kind of standard, SAIFI.
Yeah. How about the SCADA system? is differed with the smart grid?
SCADA, no. SCADA is just a traditional metering system. So in my second lecture, I mean tomorrow, I will introduce SCADA and and its difference with between the PMU. Yeah, SCADA is just a traditional metering system.
Okay. I mean, it have a supervisory control also, right?
Yeah, it's called supervisory control and data acquisition. It is not only for power grid, but all the industry system, it must have such a SCADA system, but it can only take the low sampling rate data. And the data is not synchronized either.
Achha.
Yeah. So tomorrow in my second lecture, I will introduce this.
Okay. Any questions from the participants? Yeah, you can
Yes,
unmute
please.
yourself.
Can Energy consider as a modern smart grid with paradigm? I think so. I think the most important difference is that Energy Internet will consider other energy carriers, energy systems, transportation systems, and the gas systems. So this one shows a difference. Most importantly, I think is other energy system together. And the student asked which software are used for smart grid. Okay, that depends on your, target. If you are looking at the power grid analysis, certainly we have different offline software for system power flow study, stability study. So for my research group, we are using PSSE and Dig Silent. That is mainly for, I will type it here, and Dig Silent. Most of these two are very popular in USA and European countries, Australia, Singapore as well. So they are for the power grid study. Yeah, and then if you are looking at the system planning, sometimes they use Homer. Okay, Homer is also a good tool for planning. Yeah. And for simulation, cybersecurity point of view, okay, for simulation, if your concern is on the communication system, there are different simulation software for the communication system. For my group, we are using a software called I forgot the name. I actually forgot the name. It's called the. Later, I will check. We have actually built a coupled system with power network and the communication network. Power network, we are using PSSE and Dig Silent. And the communication network is called, later I will check the report. I will let you know tomorrow.
You can unmute yourself, Chandra Reddy.
Yeah. And yeah, another question, what are main challenges the rising smart grid engine apart from cyber attack is possible to certify the rising load? Yes, a very good question. I think another very important concern instead of cyber attack is here, is how can we dispatch and operate our system without compromising the security. You see the power output of the renewables, they are fluctuating. How can we dispatch our system? How can we control the frequency? Right? And because the power converters system dynamics are different, how can we maintain the stability? They are all challenging topics. Yeah, cybersecurity is just the one part. Yeah, to achieve net carbon neutrality, certainly we have to increase the share of the renewables. We have to retire the traditional fossil fuel power plants. But as a cost, how can we maintain system stability, control frequency, right? Dispatch the system will be the challenging topics. That's why, researchers are working, right, on that topics. You suggest some literature for charging station and internet. Okay, I think for the charging infrastructure, there are a lot of good reports here in the US APRI or even IEEE transactions. In this report, we also mentioned some electric vehicles. Yes, there are quite a lot, but depending on, your perspective, are you coming from the charging infrastructure provider or you are from the power grid perspective, their focus will be different. Right? For power grid, they want to manage the charging. They want to manage the power grid to, host this charging power demand. But from the charging service provider, they want to, make a profit by providing this service. So they are looking at the dynamic electricity tariff, the charging pricing, right? The perspectives are different. Okay, thank you guys. Your questions are all very important, very interesting. I'm happy to see that.
Thank you, Professor, for being and delivering the lecture on the brief history of the power systems and then the motivation of smart grid development. And also, we have been discussed on uh, the power grid reliability performance also, and some of the definitions and structures of the smart grid, and some benefits and challenges with the smart grid. And also, we have been emphasized on the energy internet, how it is a difference between the smart grid and then energy internet also. I hope that all the participants got the advantage, I mean, the inputs of the introduction to smart grid. And tomorrow we are going to start the lecture on the introduction of energy internet at 8:30 a.m. in the morning. Thank you.
Okay, thank you. I will see you tomorrow.
Bye.
Bye bye.
The participants, you just give your attendance in the Google form, which I shared you in the chat box, please. Yeah. Thank you. Thank you very much.
Okay, thank you. I will share these slides. I will send these slides to your email, Professor Kuma. Then
Yeah.
you can share with the student.
Yeah. Yes. Yes, Professor.
Okay, bye bye. See you.
Bye.
See you tomorrow.